For millennia, the night sky was our only window to the universe. All that glittered up there seemed eternal, unchanging, unmoving. But now we have launched machines to fly among the stars, and they have returned stories of worlds and wonders. Worlds that shouldn't exist. Galaxies too young, planets too huge, structures too symmetrical, and a signal steady. One of Webb's first targets was a supernova remnant. It was 10,000 light-years away, and officially designated Cassiopeia A. The supernova had occurred 340 years ago, and the remnant was fading fast. Webb was able to study this planet in unprecedented detail thanks to the transit method. This technique involves observing the dimming of a star's light. As a planet passes in front of it, Webb analyzed the starlight passing through WASP-39b's atmosphere and detected unexpected water vapor. Positronium is formed when a positron, the antimatter counterpart of an electron, meets an electron and annihilates. It's a bizarre state of matter that exists for fractions of a second before it annihilates again, releasing energy. Webb detected this energy release in the form of gamma rays, validating theoretical predictions that had so far remained untested. The implications are profound. Together we can explore more of the universe's wonders brought to life by Webb and other groundbreaking missions. We'll delve into the latest discoveries, unravel the mysteries of space and time, and consider the profound questions that arise when we gaze at the stars. Join me in the pursuit of knowledge, and let's continue this incredible journey together. Understanding matter-into-matter interactions is vital to unraveling mysteries. Like the matter-into-matter asymmetry in the universe, why is there more matter than antimatter? And Webb is providing an invaluable window into these processes. Now, detecting water on a planet outside our solar system is remarkable. The discovery and characterization of exoplanets have been one of the most significant achievements of recent astronomy, and Webb is poised to take this research to new heights. Using techniques like transit spectroscopy, Webb can analyze the atmospheres of exoplanets. By studying how starlight filters through these atmospheres, Webb can identify elements and compounds present on these distant worlds. This has led to the confirmation of sodium in the atmosphere of WASP-39b, an indication of possible water vapor, and the analysis of WASP-1 to be a scorching hot gas giant orbiting an extremely bright star. Webb detected clear signs of water vapor in WASP-12b's atmosphere, bolstering the evidence from WASP-39b. The implication is profound. These findings bring the search for extraterrestrial life closer to home. While life as we know it might not exist on these inhospitable worlds, they offer clues about conditions under which life could potentially emerge. Water is considered a key indicator of life because it's essential for life as we know it, but it poses a puzzle. It's a reminder that the universe rarely ceases to amaze. As Webb ventures deeper into the cosmos, it will continue to rewrite our understanding of the universe, forcing us to confront the profound realization that we may have only scratched the surface of the grand tapestry of reality. WASP-39b is extremely hot, orbiting its star closely. How could water exist in such high temperatures? Astronomers believe WASP-39b could have a magnetic field that blocks charged particles from its star, creating a protective atmosphere. But this challenges existing models of exoplanet formation and requires further investigation. Astronomers wanted to observe this because they'd seen the same supernova 300 years before with the naked eye. From pulsars that skip beats to planets that defy temperature, the universe appears to be rewriting the rules. Is this a sign that our models are incomplete? But it's equally fascinating to explore the parts of the cosmos that Webb confirms do fit into our theories. Take, for instance, the analysis of the cosmic microwave background. This is the radiation left over from the Big Bang, the universe's primordial soup. Studying this radiation gives us a snapshot of the universe, as it was just 400,000 years after the Big Bang. Webb's instruments were sensitive enough to detect minute variations in this radiation, and what it found was astonishingly precise. The temperature maps of the CMB that Webb produced were accurate and detailed, confirming our understanding of the universe's early days. This level of precision is crucial. It validates our theories about the formation of galaxies and large-scale structures in the universe. Or are we witnessing a cosmic game of hide-and-seek, where nature is playing by her own rules? Webb is unraveling the threads of a cosmos more intricate than we ever imagined. And as it continues its mission, the patterns it reveals might lead us to a truth that's both humbling and terrifying. They called it a new star, because it appeared and disappeared within months. But Webb showed them something nobody expected. The remnant was oval-shaped. That implied that Cassiopeia A exploded in a direction pointing right at us. With no other supernovas to compare it to, it was impossible to confirm that hypothesis. But Webb's data offered a tantalizing glimpse into the nature of these explosions. As more data came in, it became clear that the supernova had been of type 1A, a class known for consistency and brightness. This type was first seen in 1054. This makes them useful as standard candles for measuring distances in space. The universe is vast and galaxies are incredibly far apart. It's difficult to determine their distances. Measuring the brightness of a known explosion helps astronomers gauge how far away a galaxy really is. By comparing a known brightness with the apparent brightness, they can calculate distance. But the key assumption is that the supernova behaved the same way each time that the explosion is consistent. Well, the data suggests that may not always be true. There was something unique about Cassiopeia A that made it brighter than expected. It's making its distance underestimate, and that raises questions about other supernova that astronomers have used to chart the universe as expansion. Rhythmic and unnatural, that doesn't fit into any known astrophysical model. This isn't just another discovery. Neutron stars are the dense remains of collapsed massive stars. Some of them spin, and as they do, they emit beams of radiation. Astronomers call these pulsars because they pulse like a cosmic lighthouse. It's well established that pulsars slow down over time as they lose energy. But Webb observed an extraordinary slowing down in a pulsar called PSRJ 174822446 AD. Located in the M81 galaxy, this pulsar was studied extensively by Webb. It revealed that the pulsar is losing time dramatically faster than expected. It's losing a full second off its rotation period every year. That's the equivalent of Earth's rotation speeding up by 5 days every 100 years. This is important because it challenges fundamental models of physics. Our current understanding of how pulsars work relies on equations and models. But if they're incorrect, that could have repercussions for broader physics. It's a collision between what we believed and what actually is. Our instruments are whispering tales of a cosmos rewritten, of rules bent and realities reformed. Are we seeing the birth of a new universe, or a glimpse of something far older? This is a journey to the heart of an unfolding mystery. This is the cosmos, according to Webb. In 1996, the European Space Agency embarked on a mission to construct a telescope. So powerful it would peer back through time to witness the universe's first galaxies. Fast forward 2 decades, countless technical hurdles, and one epic battle with NASA to launch the James Webb Space Telescope. What followed was immediate controversy. When it began operation, Webb captured stunning images, each one pushing the boundaries of what telescopes had shown us before. It saw the farthest we had ever looked into space, and the oldest light we've ever detected. And as the dust settled on Webb's glory, astronomers started noticing something strange. For centuries, humanity has gazed upon the sky, constructing theories, formulating equations, and imagining our place in a grand cosmic puzzle. But all of our physics, cosmology, and understanding of space and time has been shaken to its core. For example, in the quest to measure the rate of the universe's expansion, astronomers discovered that distant supernovae were dimming slower than expected. This threw them into turmoil. Our equations said the universe should be accelerating towards a heat death, yet the numbers weren't matching. Enter the hypothetical dark energy, an invisible, repulsive force that counteracts gravity and accelerates expansion. Dark energy was a theoretical solution to an equation that didn't add up. But as Webb delved deeper into the cosmos, it hinted that maybe the answer wasn't always in the unknown. One striking example is the peculiar case of supernova. Another anomaly that Webb has helped uncover is the changing behavior of neutron stars. And then there's the peculiar case of WASP-39b, an exoplanet. What's happening out there seems to be more than meets the eye. So far, we've looked at some areas where Webb's data contradicts our current models. In addition, Webb confirmed the existence of a mysterious substance called positronium. But perhaps most exciting is Webb's contribution to exoplanet research. James Webb is more than just a telescope.
Hi.
It's a bridge between what we thought we knew and what we're discovering. If you've enjoyed this video, I invite you to join me on a platform.